so last time we got started in section 2.2, and we had gone through a few things so far, and some notation is one of the issues we've gone through, also counting numbers of items within sets, so they're called elements, and I believe that we're on that one. Does that look right? Okay. So today we're going to talk about Venn diagrams, and we're going to talk about how we can use them to help us sort of solve logic puzzles. That's the kind of idea that we're going to take a look at today. So first of all, Venn diagrams are used to illustrate ideas in logic. And Venn diagrams in their simplest form are used at very, very young grades. I remember my daughter coming home in second grade and drawing me a Venn diagram and telling me what they used it for at school. It wasn't related to math, but the idea of a Venn diagram is used very early on. What we're going to be using it for is to solve logic puzzles, so that's a little bit later elementary school. But a universal set is a set that contains all the elements being considered. So when my daughter was doing this particular activity, they were talking, they had a person that they were paired up with, and they were talking about characteristics that she and her friend had in common and things that they had that were not in common. So the universal would be simply all the characteristics that either child had. That would have been the universal set. Or actually, it would actually be all the characteristics possible for any of the children would have been the universal set. And then when we're talking about the complement, we're talking about a set that is defined as F. Make sure I use the notation your book uses, with a bar on the top. That's how your book defines it. If you've seen it before, you might have seen it defined with a prime notation, or sometimes it's defined as what looks sort of like a superscript C for complement. Your book is going to use a bar. And this is all of the items that you're under consideration that you don't have in your set. So for instance, if we talked about all of the students at OBU right now, the complement for the group in this classroom would be everyone who's not in this classroom. Right? All the OBU students who are not here in our classroom right now. And I want to show you what a Venn diagram would look like in terms of drawing this. So a Venn diagram starts out looking like a rectangle, okay? And inside the rectangle, you place the circles. The number of circles will depend on the number of things you're comparing. So for what we're working with, we'll place either 1, 2, or 3 circles inside of our diagram. And they overlap. So I'm going to draw one circle right now so that I can show you this idea of complement. If this circle is F as defined here, then F complement would be everything on, sorry, use the notation your book does, right? Okay, that wasn't what I wanted. F complement would be everything on the outer side of the circle. Okay. All still within this big old rectangle, this box. This box is considered the universal set U. So that's the whole universe. So if we said our universe was, well, I'm going to do the example next actually. We'll just do it. If our universe is the set of all OBU students, and A is the set of the graduating seniors, then what would A complement be? Right. So there's two pieces in what Taylor said that are important. Number one, she described the fact that it is the students still that we're talking about. So we still have to describe it in terms of what the universal set would be. So this would be all, can't write today, my goodness. All OBU students. Okay, so that's the universal set. The complement part then is the part where it describes what is not A. That is, what is A not going to be satisfied, or what is not going to be satisfied because you're not an A. And so in this case, it would be who are not graduating. And we'll just use the same term that they did. They're not graduating seniors. Okay, so you should be able to do this and be able to create a set and a complement pretty easily. All you have to do is define what you want first you have to define what the universal set is going to be. So you could define the universal set to be, for instance, all the people in my family. Right? So if I do all the people in my family, I know I gave this example last time. If the universal set is all the people in Dr. Man's family, and we have the small circle, and the small circle is defined as the adults, right? That would be my husband and I would be part of this inner circle. Then the complement would be all the children, all the non-adults in the family. Okay, so you can do this with any kind of an example you'd like. You just have to define basically 3 pieces of information, right? Define the universal set. You have to define what your category is inside of the universal set, and you have to be able to describe what is not in that category. And we can make this relationship. We also have something called a subset. So a subset is simply a set inside of the set you're talking about. So if we have sets A and B is a subset of A, we actually write it like this. It almost kind of looks like the less than or equal to notations you've seen before, but it's not a less than sign, it's a contained in sign, so it's curved. And what that means is that everything in B is an A. Everything in B is an A. So I could sort of describe, for instance, maybe that my set A is my whole family, like extended family and everything, okay? And then the set A that's inside of it could be my immediate family members. Right? My immediate families are all part of my extended family as well. If my extended family is, think of a family picture, right? You guys have seen these happen before, where you get the whole family in the one picture, and then you take pictures of the little individual pieces of the family in pieces, right? Well, all those little pieces of the picture, those are subsets of the big, larger picture that you're talking about. If you want to talk about a proper subset, which is actually how I've been describing this, a proper subset is actually a set where this A and this B have the same relationship. All of everything in B is an A. But we also have at least one element in A that we didn't talk about in B. So this says for all sets A and B, B is a proper subset of A. That's actually written like this. It doesn't have the little line on the bottom. It's almost kind of like eliminating the or equal to possibility, because that's kind of what that notation looks like. If and only if all of the elements in B are in A, okay, that shouldn't look like less than or equal to, it will get curvy. Let's try again. So all elements in B are in A, and B does not equal A. So as odd as it would sound, I could actually describe my immediate family as set B, and I could describe my husband's immediate family as set A, and we could say they're subsets of each other. Well, I mean, that sounds weird, because we're just talking about the same group, right? We're saying they're exactly the same. There's no differences whatsoever in our two particular families when we describe them as our immediate family. And so they'd be subsets, but they almost feel odd to describe them that way, right? It feels a little weird. They would not be proper subsets because they are equal, right? This actually says they can't be equal for them to be proper subsets of one another. We'd have to have at least one member of the family in one of our descriptions, not included in the other person's description. So we could talk about one of my stepbrothers who has children from a prior marriage, and then that would actually work, right? So if one of my sister-in-laws who's married to one of them talks about their immediate family, they may or may not include the estranged stepdaughter that they've never really spent any time with. But my brother-in-law might, because that's who he might actually consider her part of his immediate family. So his immediate family would look a little bit bigger because it includes that extra daughter that's not really a part of their immediate lives. They might have some kind of relationship like that. When we're talking about the number of subsets and the number of proper subsets, there's a real quick way to figure out how many subsets and proper subsets we're talking about. So if a set has n elements, okay, so like my family has 4 people and 5 people in it, sorry, 5 people in my family, then there are 2 raised to the n power, so 2 to the 5th subsets. So we could talk about the subset that's all girls and it's all boys. We could talk about the subsets that have 1 person in it, or that have 2 people in it, or have 3 people in it, or have 4 people in it, or have 5 people in it. We could talk about breaking them apart into these different groups. And the number of different groupings, subsets, that we have is 2 to the 5th for my family. And I feel like I left something out or put something in the wrong place. Okay, so there are 2 to the n subsets, and then there are 2 to the n, and then minus 1 proper subsets. So a proper subset can't include the whole set itself, although that is a subset by definition. So there's 1 fewer subsets that are proper subsets than there are subsets. So in my family, if we did this, if we wanted to know how many different subsets could we create, well, we could create subsets that have 1 person in them, right? This would be like everybody needs a little bit of alone time in their own bedroom, or in some room of the house. We've got subsets. We've got subsets of 2 people in them, so everybody needs a buddy, grab a buddy's hand kind of thing. We could talk about subsets that have 3 people in them. We could talk about subsets that have 4 people in them. That's what happens when, dad goes away on a business trip or something, right? Or we could talk about subsets that have everybody in them, and that's a subset, but it's not a proper subset, so we need to exclude that one for counting proper subsets. In terms of how this works in practice, If we were looking at this for my family, we'd have 2 to the 5th, which is what? You guys remember? 2 to the 5th? You're close. It's the next one. What's 16 times 2? 32. There are 32 subsets that I could create within my family of 5, because that's 2 to the 5th. And then proper subsets would be 1 less, so it would be 31. So let's do another example here. Consider the set of all OBU, a set of all math faculty at OBU, and there are not 4 of us anymore. This was from last semester. Oh my goodness. There are 5 of us now. Ooh, I should fix that slide. There are now 5 of us. So this is the exact example that I just did. Have fun, we've already done it. All right, so how many subsets are there? Well, 2 to the 5th, there are 32, you got it. And how many proper subsets? 31. The question on number 6 is a little different. It says, suppose you have a set, and the set you know has 127 proper subsets. The question then is, how many elements are there in that set? So you could do trial and error, right? You could actually say, sounds like maybe there's a bunch. I mean, 127, that's a lot. Maybe I think there's 10 in the set. And you could take 10, 2 raised to the 10 power, then minus the 1, and see if that's 127. So you could go through some combination of those things. That's a problem-solving strategy that would work. What else maybe could you do? I know you guys know how to guess in chat, so I was trying to think if there's anything else you could think you might try.
I would set up an equation.
Okay. Shelby, I think that's a really good direct way to do it. What did you have in mind?
127 equals minus 2n.
I think you mean 2n minus 1.
Yeah.
Okay, that's good. Okay, so basically the 127 is the information we were given, right? And it's supposed to equal the number of proper subsets, and this is that formula for the number of proper subsets, 2 to the n minus 1. So what would you do next to solve that formula?
Add the 1 over.
Okay.
I would make 128 and raise 2 to the power.
You can do that, yeah. So this is where the trial and error a little bit is going to come back into play. So you're going to grab your calculator, and your question is going to be, what number needs to go right here to make 128? So you're going to try. You're going to say, how about we do 2 to the 10th? How about we do 2 to the 4th? How about we do 2 to the 20th? Whatever you're going to try. You're going to try something, and you're going to find that one of them is 128. Do you know which one? It's 7. So the number 7 in here actually makes this work. So this is actually n equals 7. There are 7 elements in my set. And you don't have to do it from this perspective. Trial and error flat out from the beginning is fine. But basically the issue is that if you take 2 and you raise it to the power of 7, and then you take 1 away, you will get the number 127. So that 2 raised to the power of 7 gives you that. And then, so the 7 is the issue. We've got 7 elements in my set in order to make this work. Any questions on that one? All right. This problem is a combination problem. When you do this on your homework, it's going to ask you on one problem to decide which of these 2 go in statements like this. And on the second problem, it's going to ask you to decide which of these 2 go into statements like this. So it's not going to ask you to do all 4 things on the problem. Is that okay with everybody? I just wanted to consolidate it to do it just with the same grouping of questions. So we're going to do this problem twice. The first time we do this problem, we're going to answer the question as though it's the red question. And the second time, we're going to do the question and answer it as though it's asking us about the blue question. Okay? So first question we want to know is we want to know which of these 2 symbols should go in these blanks. So let's talk about these symbols. Do you remember what this symbol was? It's an element of, right? Is an element of. What do you suppose this one is? I don't think I actually defined that one yet. It's not an element of. Yeah, you draw a slash through anything in math and make it not something else usually, with very few exceptions. Okay, so we've got to decide if the first item is an element of the second one. That's the issue. So over here, this right here this empty, or this notation right here, what does that mean? That's the empty set. Now, there's a really important word that I just wrote down right there. That word that I just wrote down that's really important right now is the word set. Sets are not elements. They're sets. Okay? So the symbol that has to go between this by default is the symbol that looks like this, because the first thing in the description, it isn't an element to start with. So we can't even talk about whether or not it's actually in the next set. It isn't an element. Are you guys with me? If it isn't an element, it can't be an element of anything else. Right? We can't talk about me being a boy because I'm not a boy. It doesn't even make any sense. We can't talk about this being an element of something else because it isn't even an element. The second one, though, actually is, right? This is a number. It's a single value. It may or may not be included over here, but it is an element, potentially. We just don't know if it's an element of what comes next. So what we've got to do is we've got to figure out what in the world this notation actually means. Okay, so that's set builder notation. We encountered it last time. We haven't done anything with it, I know, yet. But if you'll remember, what it says is this is all x such that x equals 2n and n's a natural number. So let's talk about what this actually means. Well, actually, you know what? Let's even break it apart smaller than that. Let's talk about what this means. What does n, an element of capital N with a double line, what does that mean? Right. Natural number, very good. That's what that capital N notation means. So these are the natural numbers, like 1, 2, 3, 4, 5, 6, 7, they're the counting numbers. And then this is telling us what are we going to do with those counting numbers? Multiply them by 2. So if you take the numbers 1, 2, 3, 4, 5, 6, and you multiply them by 2, what do you end up with? Even numbers. So this descriptor over here, these are even numbers. That is a description of how even numbers come about. That's all it is. So the question boils down to, is 15 an element of the even numbers? And the answer is no, it is not. So this is not an element of this set. C also could be tricky if you're not paying attention. What do you see on C that makes it look distinctly different than B from the very beginning? Brackets. Very good, Nicole. There's brackets around there. Those brackets around there mean that this, again, is a set. We put sets inside of brackets. This is a set. It is not an element. So I don't care what the right-hand side actually means, because this can't be an element because it isn't an element of it. I mean, it's just not an element at all. So this is not an element at all. Okay, how about the last one? What do you think? Yeah, that one works. Finally, we've got one that's an element, right? This is an element because 16 over here on the left would be included if we continued the dot, dot, dots. These are the even numbers described out with more depth, right? Okay, is everybody good with this one? With the right, because I'm going to erase it and I'm going to do blue. Okay, so this is what we would be looking at if we were trying to decide if something is a set, or is an element, or is not an element. Okay, this notation we encountered today. What did this notation mean? Subset. And what it really means is that if you've got sort of this A subset B, it means that everything in A is in B. That's what it means for, and it has to be a set because we're talking about sets here. These are both sets. A and B are sets. I mean, we just kind of like the issue with a minute ago with elements. If it's not an element, we can't even talk about it being an element of something else. If it's not a set, we can't even talk about it being a set of something else. It doesn't make sense. So this is not very dark up here, but hopefully your paper it printed out a little bit better. It looks like that. What does this supposedly mean? I didn't define it, but I bet you know. Yeah, not a subset. Okay, so taking a look. This first description right here. This description says it's an empty set, and then right on the right-hand side, it's a set with the number 0 in it. First question you have to decide is, are they both sets? And the answer is yes. So we at least stand a chance at being able to put that symbol that's a subset between them. Now here's a fact that you will want to write down for yourselves to remember. The empty set is always a subset of every other set. So as long as you're talking about two things that are sets, the empty set is a subset of it. It's simply the set with nothing in it, right? We can talk about those wonderful, wonderful college students that live at my house and how wonderful they are to do the dishes and to clean up after my pets and to whatever. It's a subset. It can be described, but there's nothing in it. But it's still a subset, right? It's the number of people right now that are sitting on my bed. It better be 0 because everybody's out of the house. Right? That's an empty set, but we can talk about it. All right, the second one, part B. What's going on part B?
The left side is an element.
The left side is an element. Let me start with what you just said there at the beginning, Shelby. The left side is an element. So what's wrong with that? It's not a set. This feature right here is not a set, so there's absolutely no way it can be a subset, because in order to be a subset, it first has to be a set. So it really makes no difference in this particular one whether it is or is not included in what's ever on the left or on the right, because it's not a set to start with. It's a notation issue, right? It can't be a subset if it isn't a set. Now on C, it is a set, right? I mean, these are both sets. So at least, again, like on part A, we have a chance of putting the symbol between them that says subset, because they are both sets. Let's actually think about what this set really is. This set says that it's the number 1 plus 2, 1 plus 3, 1 plus 4, 1 plus 5. What's another way we could write that set?
3, 4, 5, 6.
Okay. So is everything in the set on the left, whoops, touched a screen somewhere. Is everything in the set on the left contained in the set on the right? Yes. The only thing that's in the set on the left is the number 4, and that element 4 is in the elements that are on the right set. So this one is a subset. Everything in the first set is contained in the second set. What about D? Doesn't work. Why not? It's not a set. It's an element of it. That's fine. That's not the question we're issuing, that we're addressing at the moment. Okay, are you ready for the next slide? All right. I thought that we got to it later in this lesson. I talked about this last time. Do you guys remember? We had a question at the very, let's see, where was it? Example number 2. Example number 2 said, how many one-to-one correspondences are there between two sets of 6 elements each? You guys remember that one? And we said it was 6 times 5, which is 4 times 3. And this is an application of the fundamental principle of counting. So the fundamental principle of counting says the following: if you can have one event, event M, and it can occur in little m number of ways, and you have another event, event capital N, that can occur in little n numbers of ways, then if you take event M and you follow it by event N, how many different ways could this event be performed? So imagine if you wanted to talk about getting clothing out of your closet, all right? You've got to choose a shirt, you've got to choose a pair of pants. Okay, that's all we're going to limit our discussion to, pants and shirt. And everything matches. Okay, so it's equally likely that you could pick whatever, all right? Well, then what you would do is you'd say, well, how many different shirts do I have? Okay, maybe it's 15. I have 15 shirts. How many different pairs of pants I have? Okay, maybe it's 6. I've got 6 different pairs of pants. Well, I take 10 or 15 rather times the 6, and that would be the number of different outfits that I have in my closet. And that's what this is describing. This is describing how many outfits I would have in my closet if I did something like that. And we could continue the process, because we could also say, and I have 5 different pairs of shoes, and I have this number of belts, or something like that. We could create a different outfit by describing it in that way too. We just continue the process. So here's our example that it gives us about 4 digits. We've got 4-digit phone number extensions. So if you have 4-digit phone number extensions, there are 4 different choices that you have to make, right? How many different digits do we have in our number system? 10, because we get to include 0. Yeah, so we would actually include 0. So we have 10 different choices that could be the first digit. How many choices do we have in the second digit? Still 10. This one doesn't happen like the example we had last time, because if we repeat it, we're allowed to repeat a digit, right? And then we have 10 here, and we have 10 here. And what happens is we're supposed to multiply these together. So if you had 10 times 10 times 10 times 10, what number is that? So if you're thinking about sort of like a campus phone extension, I don't think you guys have phones in your rooms, right? Because everybody assumes you have a cell phone these days. When I was a student, we had actual landline phones in rooms. So if you actually had sort of the first 3 numbers, assigned to you by the phone company or whatever for your campus phone system, you could actually have 10,000 different campus phones, which would actually be able to be used in your campus system. That's what this is telling you. 10,000 different numbers that you can use. What if you can't repeat digits? Now that doesn't really make a lot of sense with the phone system, but let's talk about what would happen in terms of the description of how we would do this. So the first digit, you would have how many different options? 10. But if you can't repeat digits, then the second digit you would only have 9 choices. The third digit, 8, and the fourth digit, 7. So someone grab a calculator for us and let's multiply this out. 10 times 9 times 8 times 7.
5,000.
Half as many. All we did is say we can't repeat something when we have half as many options as we had before. That's a big difference, isn't it? All right. Now some things make sense that you can't repeat, right? But the example that we did on example 2 is we were trying to do pairings of people, right? So if Susie is dancing with Dave, then Jill can't dance with Dave at the same time. So those pairings have to be in that way. So there are things that make sense that we can't repeat. And there are things that make sense that we should be able to repeat, like numbers in an ID number or a driver's license or something like that. All right, last example. How many different ways can you go to your Can you go to your 5 favorite stores in the mall if you only get to go to 3 of them? Okay? So we're going to go to 3 stores. So very much like on the last slide, I'm going to actually write down 3 lines. How many different options do I have for my first place I'm going to go? 5. Would it make sense to go to that store, to come out and walk back in? No. So we're not going to repeat, right? So how many options do I have for my second stop? 4. And then the last stop, 3. Okay, so you're making the decision most of the time on whether or not repeats make sense. Usually, I'm not going to tell you. It's something that you should have to be able to read through and say, yeah, I can't repeat the digits here. So this is what I would do instead. All right, so what is 5 times 4 times 3? So there are 60 different options or combinations that you could choose from among your 5 favorite stores if you're only going to go to 3 of them. What if you get to go to all 5 of them? Right, 5, 4, 3, 2, 1. So how many different ways can you make a decision of on this one? 120. Okay, so this is the number of different ways that you could actually go into them. So maybe you go to Old Navy first, and then you go to Kohl's, and then you go to Bath and Body Works. But then if you do it in a different way, then that's a different ordering. Okay, so that's what we're counting up here. Last example I want you to do. So do you guys have new group work partners? Did I do that last time? Like probably none of them are here because half the class is gone. But what I'd like for you to do, for starters, and I'd like for you to find your group work partners. I'm going to pause this for just a second. All right, so it took a moment here, and you guys created null sets. So somebody share with me the null set that you and your partner created. Audrey.
The amount of children that Nicole and I have.
The number of children that you have. Okay, so you wouldn't actually say number, you would actually describe it as the children you have.
Oh.
The number is actually ends up being 0, right? That's the cardinal number. Just like in mine, I wouldn't say the number of children that are college age live in my house. It's just the children that you have between you. 0, that's good. What else?
The guys living in a girl dorm.
The number of males living in a female dorm. Okay, and again, we would say the males living in the female dorm. Good. What you guys get?
We did the opposite. We did all the girls living in AG.
Okay, the girls living in AG, and you said it right without the word number in there. So the number, actually, the cardinal number would be 0, What you guys get back?
The people who live on the moon.
The people who live on the moon. Very good. You know what? You guys are the first group who hasn't described something like the number of boyfriends I have. For some reason, that's a popular one usually when I get to this point. I don't know why.
That's hilarious.
Yeah.
They're bitter.
Maybe that's the problem.